Good morning. We are moving on to chapter 6. So we're going to take a closer look at gravity, gravitational forces. I know we've already looked at this, right? But we're going to look at it in some more detail. In particular, we've spent a lot of time talking about gravity and how what the effects of gravity are near the Earth's surface. But now we want to look at locations that are more distant, and not just the Earth's gravitational field, but gravitational fields for other planets, stars. So let's take a look. So here's a list of, the usual list of topics. And as always, I'm a little concerned about weightlessness. We'll talk about what weightlessness means. And then always, my emphasis, I guess, too, the little g, I'm going to refer to that as the gravitational field. And so, and that's what I've been doing so far. So let's go ahead and get started with this. So the formula that we use for gravity dates back to Newton. Now we have more recent descriptions. We have a more recent, actually more complete description of theory of gravity called from Albert Einstein, which is general relativity. We're not going to use that in this course, and the reason why is mathematically it's like a million times more difficult mathematically than the formulas that we've been using. So anyway, we're going to be using a formula of gravity that Newton developed, and it works great except under extreme conditions. And we know where those extreme conditions are, so we can be careful and make sure that we're using the Newton's laws of gravity in situations where it's going to work very effectively. So what this is pointing out is, it's asking what would be the source of the gravitational force that we experience. Now they've got people standing at different locations and maybe making measurements gravitationally of objects, and you realize, if Earth is like a sphere, and all these different people, wherever you go, gravity behaves kind of similarly, there must be some central force acting here. Now, Newton's approach was to say, look, the gravitation effects that we experience near the surface of the Earth, what if those are the very same forces that hold the planets in place? So this is kind of a remarkable synthesis of ideas. And so what Newton found out, what Newton realized, is let's say that gravity, there's a gravitational force, and that it's attracting the Earth and the Moon, and that this is one of those force pairs where Earth is pulling on the Moon with a certain gravitational force, and the Moon is pulling on the Earth with a certain gravitational force, and those forces are equal in magnitude and exactly opposite in direction. And Newton's approach was to say that this force would be attractive, that it would tend to draw the two objects directly towards each other. And that's the model for gravity that we'll be working from. Now, what's kind of interesting here is you might say, well, who's experiencing the larger force? The Earth has a lot more mass than the Moon. Earth is like 80 times the mass of Moon. And does that mean that it experiences a larger force? Does that mean that it exerts a larger force? And what Newton found was the forces are the same. So both objects experience the same amount of force. The magnitudes match. So that's a very interesting feature. Now, here is the formula itself. There it is. It's highlighted. And this is a formula that Newton came up with. Now, it's not super complicated. It says that the force of gravity depends on the masses of the two objects. So, we can take any two objects and ask how much of a gravitational attractive force is there between those two objects. The items we need to know, how much mass does each object have, and then what's the distance between them. Now again, this is another example. We've seen this before. A lot of times in physics we are using r to represent distance, not radius. So you got to train yourself not to think radius. Talk to yourself. When you're doing these problems, say r is distance. That's what it's keeping track of. And so this is the distance between the two objects. And we think of it as a center-to-center distance between two objects. And then to kind of finish out the formula, what Newton needed was some kind of a constant. These are in units of kilograms, for example. This could be in units of meters. But the force is going to be in newtons. So we need some kind of a force constant to tell us just how strong is the gravitational force, and that force constant is going to be based on the units that we're using. So the value that we currently measure for the gravitational force constant is 6.67, 10 to the minus 11 newtons times meters squared divided by kilograms squared. So it's a lot of units, but notice the units that we have are, well, the kilograms squared cancel out the kilograms in the masses. The meters squared cancel out the distance units in r. And then the last units we have to have are newtons, because the force is going to get measured in newtons. So that's what the gravitational force formula looks like. That's the gravitational force constant. Now notice how small that number is. So it turns out that gravitational forces are not very significant. They're not very big forces unless you have something with a lot of mass. And so let's take a look at some of those examples. So our first example is, what is the gravitational force acting between two objects? And in this case, the two objects are, there's a 50 kilogram person and there's a 70 kilogram person, and they're sitting on a bench close to each other. Estimate the magnitude. Oh no, they didn't tell us the distance. Okay, well, we're going to have to come up with a number for that. So let's say that we have these two people. I guess they were sitting on a bench. And here, this object is mass 1 and this object is mass 2. Now remember, gravity is acting between every part of every object. So how do we combine that effect for an entire object? You know, it's like the toe from here is attracting the ear from this person. So what we have to do is, to get a good estimate, is we'll do center-to-center measurements. That's going to give us, that's a good approximation. So we're going to say that from the center of this person out to the center of this person, it's about 1 meter, and then not worry so much about the details of all the other distances involved. So we got to put in the mass, we got to put in the distance, and again, I'm going to say almost every example we look at, we're thinking center to center, and then the gravitational force constant. The two masses that we were given, 50 kilograms and 70 kilograms. The distance that I guess I came up with, I have to take responsibility for this. I'm going to say the two objects were about 1 meter away from each other, and then the gravitational force constant. And as we talked about on the earlier page, now that kilograms is squared. That is missing a square. That needs to get added back in. These 2 kilograms here are going to cancel these kilograms, and then the meter squared from here will cancel the meter squared, and we'll be left with newtons. So we definitely need to get a square added to the kilograms in that calculation. So the units have all canceled out, and we're left with newtons. Now when we do the numbers here, it works out to be a force of 2.33 times 10 to the minus 7 newtons. 10 to the minus 7. That's not very big. That's a fraction of a millionth of a newton. So, you know, that's why everyday objects aren't all clumping together. The gravitational force constant just isn't that large. The gravitational force between everyday kind of objects is just not very large. So I wrote that as 2.33 10 to the minus 7 newtons. I rewrote that over here as in terms of nanonewtons, where nano is 10 to the minus 9. So, you know, it's a couple hundred nanonewtons. It's not a very big force. It's a pretty small force acting between kind of everyday size objects. Now, what about, though, when we start looking at distances that are much larger than, well, let's say the size of the planet, some, you know, distances that are that large. So let's ask this question. What happens if we have a spacecraft? It's orbiting Earth. We'll say it's a circular orbit. And so it's a big circle surrounding. Now, the distance that they say the spacecraft is at is measured from the center of the planet out to where the orbit is 2 Earth radiuses. Now, that's a distance, but these are in terms of Earth radiuses. Now, they're telling us the Earth radius is at 6,380 kilometers, so we want to double that number. We want to put a factor of 2 into that. So anyway, that's the distance we're going to be looking at. Now notice, the key here is we're not measuring from the surface out to this object. We're measuring from the center. So, and then the mass of the Earth is given in this too. The mass of the Earth is given as 5.98, which is about 6.0 times 10 to the 24th kilograms. All right, let's take a look at this. So I'm going to set up a diagram. Now remember the distance that we want. I'm going to use a big R for the radius of the Earth, and I'm going to use little r for the center-to-center distance between the Earth and a spacecraft that's in orbit. Now, r is distance. R is equal to 2 times big R, and big R was given as 6.38 10 to the 6th meters. So when I double that, I'm getting 12.76 times 10 to the 6th meters. The mass of the spacecraft is listed at 2,000 kilograms. The mass of the Earth is listed at 5.98 10 to the 24 kilograms. And then the gravitational force constant is given. And look, the units, I think I got the units right. So this is what the formula looks like. Let's plug stuff in. There is big G. Here is the mass of the Earth. Here is the mass of the spacecraft. And then here is the distance squared. So I took all of that. Again, the kilograms squared here cancel with the kilograms squared here. The meters squared here cancel with the meters squared. And I'm left with newtons. And it worked out to be 4,900 newtons. Now, we can ask this question. What's keeping that satellite in orbit? And you go, oh, it's the gravitational force. We're in chapter 6 now, and we're going to be able to go in and write down equations that show how the gravitational force is holding objects in orbit. And so there's a force acting on both objects. The satellite experiences a force of 4,900 newtons. The Earth experiences a force of 4,900 newtons. For the satellite, that's a good amount of force. That's going to have a significant effect on the satellite's motion. You know, for the planet Earth, 4,900 newtons, it's not a big deal. So Earth is not going to be jostled around by 4,900 newtons. Now, we said that this is a circular orbit, so we'll get the circular orbit drawn in or imagined, and hey, this lines right up with chapter 5. So if I've got a satellite in circular motion orbiting the Earth, and there's a force of 4,900 newtons, what's the acceleration for that satellite? And we can take that force, divide through by the mass. Now the mass of the satellite was 2,000 kilograms. And so the acceleration for the moon, 2.4, not for the moon, for the satellite, sorry, 2.45 meters per second squared. So now that reminds me of the gravitational field. And this is the gravitational field that Earth's is providing at that location. So at the Earth's surface, that would be 9.80. But out in space, 2 full Earth radiuses away from the center of the Earth, that has now dropped. So what would have been 9.80 at the surface is 2.45 meters per second squared at the location that we're looking at. Now, what about the Earth? How much of an effect will this have on Earth? And not much, right? This is scientific notation, 10 to the minus 22. That's tiny, 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 tiny. So the Earth experiences the same amount of force, but its effects are really tiny because the Earth's got so much mass. 4,900 newtons acting on the Earth, no big deal. And that's giving us an acceleration of 8.17, 10 to the minus 22, and that's why we typically ignore that. All right, so anyway, we've got this spacecraft. We've been able to calculate a force, and we calculated an acceleration. So that's good. We're looking pretty good here. Here's another example that we want to take a look at. Now, this picture is a little weird because, first of all, it's nowhere near correct proportions. Now, they've drawn it this way so that we can kind of gauge how the diagram is going to operate. Let's take a look and see. So let's say that at a certain instant in time, the Earth, which is orbiting the sun here, so I got the Earth orbiting the sun, and then I got the moon. You know, the Earth and the moon can actually be treated as a double planet system. So it's not so much that the moon exclusively orbits the Earth, it's that the Earth and the moon are kind of orbiting each other around the center of mass point. Now the Earth is like 80 times more mass, and so the center of mass point is actually just a little bit off center from the center of the Earth. But the Earth does noticeably wobble due to that effect. And so they're kind of orbiting each other, and then that combined Earth-Moon system is orbiting the sun. Now, at some instant in time, they're saying that the moon is located some distance from the Earth, the moon is located some distance from the sun, the Earth is located some distance from the sun, and that, you know, from the moon's viewpoint, the force acting on the moon from Earth and the force from the sun are exactly at right angles to each other. So this is, well, think about this, about how this would happen. Now, they've given us the masses. They gave us the mass of the moon, they gave us the mass of the Earth, they gave us the mass of the sun, and they're at right angles to each other. Where's the net force? So it's a chance to take this new gravitational force that we have introduced and do vector addition, basically. Now, if we were to draw this to scale, it turns out that the sun is from Earth, the distance of the sun from Earth is 400 times as large as the distance to the moon. So that would say that this distance they have drawn here is 400 times bigger than this distance. So clearly it's not to scale. And so what that also is saying is, well, let's take a look and see how the two forces compare. Because what we've got is we've got, from the moon's perspective, there's Earth, which has a lot of mass and relatively close by. And then there's the sun, which has hundreds of thousands of times more mass. But it's also 400 times as far away. So let's take a look and see. So here's all this data. Here's the mass of the moon. I'm calling the sun big M, 1, and Earth big M, 2. And I wrote those down. I even rounded a bit here. And then distances center to center, from the center of the Earth to the center of the sun, 150 billion meters. From the center of the Earth to the center of the moon, 384 million meters. So let's find out, first of all, how much force that is. So I don't have any vector signs here. I'm just doing G m1 m over distance squared. Now for the sun, I guess is what we're looking at. Here is the distance, the mass of the sun, here is the distance. And that force worked out, plugging all the numbers in, worked out to be 4.36 10 to the 20th newtons. Now you might be a little worried. Let's go back and take a look at this. They gave us the distance from the Earth to the, or I looked it up, from the Earth to the sun. That's the hypotenuse of this triangle. But what about the distance from the moon to the sun? And it's going to be basically the same thing. And that's because this distance is so small. Right? Again, this distance, the distances we're looking at here are 400 times larger. So I mean, you can set this up and go back and use Pythagorean's theorem and try and get a distance measurement in there. But it's going to be basically the same number. It's a good exercise to go through and take a look at. So that's what I've used for R1, is the very same 150 billion meters. And then I got the force from the sun. Now if I look at the force from the Earth, how much force is acting between the moon and the Earth? And that force, that gravitational force, same formula, we got to put in the mass of the moon, mass of Earth, divide through by the distance, the center-to-center distance squared. And that turns out to be, I think, kind of interesting. These forces are actually kind of similar. The force from the sun acting on the moon is about twice what the force from the Earth is. So, yeah, that's kind of an interesting coincidence, I guess, that the moon experiences about the same amount of force from the sun as it does from the Earth. Now, for this particular configuration, what I did, I hope I kept the numbers straight, I think I did. So, I calculated the two forces. Since they're already at right angles, what's the net force given by? I can take F1 squared plus F2 squared, add them together, and take a square root. And so doing that, I ended up with 4.79 10 to the 20th newtons. And then as far as the angles, now typically what we've been doing is identifying just one of these angles and then saying the adjacent side was cosine and the opposite side was sine, just to throw in a little different approach here. I actually labeled both of these angles, and I called this the cosine. Cosine of theta 1 is F1 over F. Cosine of theta 2 is F2 over F. So again, just to show there's flexibility in how these formulas work. This is how I have defined those two cosines of those angles, and then solving for them. One angle is 24.5 degrees. The other angle, theta 2, is its complement at 65.5 degrees. So there it is, the force acting on the moon at this particular instant. What's the net force? I mean, these are pretty reliable. Even as the moon orbits, this number doesn't change by much because it's only varying by this amount. So it gets a little bit bigger and a little bit smaller, but not a huge amount. And so this force is almost, very reliable within a small amount, and actually this one too. So those force numbers. And then it came down to looking at the angles and deciding how to combine those two forces. But that's, it's an example of vector addition for those two forces. All right, now the textbook goes through and it presents this very detailed vector setup for the gravitational force. I think it's overkill a bit. I don't think you have to go into quite that much detail. So, but I'm going to go through it. This is what they're calling a unit vector. It's got, instead of an arrow, a full arrow, it's got this little hat. It's got this little peaked hat on top of it. That says it's a unit vector. If you remember, the unit vectors have magnitude 1, and they're only keeping track of direction. And then the force, they're saying, is opposite the radial unit vector. So if these are the two objects, m1 and m2, then the unit vectors point away from the objects, and the forces are back towards each other. Now, there's a lot of detailed subscripts here. The 1, 2s and the 2, 1s. So I'm going to say that's really not necessary, as we did in that previous example. So we already did one example using this in terms of vectors, and what we did is we just divided everything up into components. So we looked at components of forces as needed, and then added them together. We never had to go back and introduce all these unit vectors. So what I said in maybe letters that are too big there at the bottom is it says use the diagrams to keep track of all the directional information. Use the diagrams, and then the math, the formulas themselves, we don't need all the vector stuff. We can just call this the force formula. We don't necessarily have to keep track of this, and that actually is a faster way to solve the problems in most situations. Now, what about gravity near the surface of the Earth? So what we've been doing is we've been using a formula mg, and that's worked, apparently, that's worked just fine, right? We introduced that, we talked about little g as being the gravitational field, and the formula now in chapter 6, Newton's formula actually is big G m times the mass of the Earth divided by the distance between the two objects. Now that's center to center, so that distance right there would be the radius of the Earth. If we measure from the center of the Earth out to an object sitting on the surface of the Earth, and again, you know, you can always, this is why, this is what we can use the textbook for, is it becomes an object. So here is an object, and what's the force acting between this object and the center of the Earth? And we need to know distances, so the distance between where this object is and the center of the Earth is, you know, given by the radius of the Earth. So what we can do now is we can actually solve for Earth's gravitational field. Here's the formula. Earth's gravitational field is big G times the mass of the Earth divided by the distance measured from the center of the Earth. If I'm at the surface, that number would be the radius of the Earth. If I'm out in space somewhere, that number could get to be much larger. Now, what they're saying here is we can kind of turn this formula around. We can take the measured value of the gravitational field, which we've talked about, the 9.80, and we can take the measured radius of the Earth, divide through by big G. This actually enables us to measure the mass of the Earth. And that's how this is done, right? So I know a lot of times students go, well, the mass of the Earth, it's in my textbook. It's just right here, right? You open up the textbook to the front, there's all the masses, those are given. But they're actually measured, right? These are masses that somebody at some point had to go in and measure these values. These are not just listed in some book. It's not a revelatory process. It's a process where you have to go out and make observations. So this is one technique. Now that we understand how these gravitational formulas work, here's one technique. We can go in and measure the mass of the Earth. All right? All right, let's talk a little bit more about gravitational field and kind of repeat some of what was on that previous slide. Chapters, really from chapter 4, I guess, chapters 4 and 5, we've been saying that the gravitational force acting on an object can be calculated, can be determined by knowing the mass of the object and then knowing what the gravitational field is. What we're saying in chapter 6 is a more detailed formula would be big G, big M, little m over distance squared, and that at the surface of the Earth, the distance that an object would be located would be 6.37. Now, this gets listed as sometimes 6.38 and sometimes 6.37. So I'm kind of going back and forth here, but 6.37, 10 to the 6th meters as the radius of the Earth. Now, the Earth's gravitational field then, looking at these two formulas, can be determined as gm over r squared. At the surface, what that gives us is 9.83. So if I use the formulas for gravitational force and gravitational field, and I plug in the numbers for the Earth's radius and the Earth's mass and the gravitational force constant, that predicts at the surface of the Earth the gravitational field should be 9.83 newtons per kilogram. Well, why are we using this 9.80 stuff if Earth's gravitational field is 9.83? And it's a rotational effect. Now, rotation, the Earth is rotating. The rotation of the Earth doesn't generate, that's not where the gravity is coming from. But what it does do is it creates the appearance, it creates an effect as if the gravitational field is 9.80, and that's kind of in the mid-latitude region where textbooks are written and where we are talking about gravity. So it turns out, if you go to the poles, the gravitational field, if you look in your table, the poles measure gravitational fields around 9.83, and then as you get closer to the equator, as you move towards different latitudes, you get different values for these gravitational fields. So for better or worse, we're taking the rotational effect of the Earth reduces what appears to be the gravity. We'll take a look at some examples with this, but that's something to be aware of. The 9.80, it's a number that includes rotational effect. It's not pure. If it were pure gravity, we'd be at the 9.83 number. Okay, here are the numbers. So these are gravitational fields measured, gravitational accelerations, let's say, measured at different locations. And what's happening here is New York and San Francisco are coming in at about 9.80. Denver also is coming in at 9.80. Notice that there's a larger elevation, but it's still not very different. Now, Pikes Peak, which is not too far from Denver, measures out to be measurably lower, and that's because you're farther from the center of the Earth. So you do see this drop-off in the gravitational fields as you get farther away from the center of the planet. Let's see what else we've got. At the pole, this is actually saying at the equator, that this is measured to be 9.78. Now, I'm not sure how much that is due to 9.78. It could be that I'm using 6.37. It could be the 6.38 number is better, and that's going to lower the values here. So this 9.80 we've been using is not as firm as we had imagined. It does include this rotational effect. At the pole, this, and they're saying it's just calculated, comes out to be 9.83. So that's the number that we came up with. Okay, so anyway, that should actually work, because that's the calculation we did. The number we did was the 9.83. The 9.80 is looking at rotational effect. So the rotational effect at the equator is going to be larger, and it's giving us that smaller number. So these locations closer to the equator are seeing more and more, a larger and larger rotational effect, because if you're at the equator, you're traveling in larger circles. In fact, here we go, effect on Earth's rotation. What's the effect of Earth's rotation on G? Okay, so here's where we have to ask, which G are we talking about? Is little g the gravitational field of the Earth, or is little g the gravitational acceleration effect of the Earth? And I want little g to be the Earth's gravitational field, but in most practical cases, that number does include rotational effects. So let's see what happens here. If we're at the North Pole, there is a gravitational force. There's a person standing here in this picture. There's a gravitational force towards the center of the Earth. Now here what's interesting is they're calling it your weight. Now this is where we talked about weight gets used differently. The textbook kind of changes their definition. What this force ought to be is it ought to be a normal force, right? But what they're doing is they're calling it weight. And what they're saying is when I stand on a scale, that's my weight. But when you stand on a scale, what you're measuring is normal force. So they're saying at the pole, north or south pole, the normal force equals mg. And at that location, you can measure the effect directly of Earth's gravitational field. Whereas at the equator, the Earth is rotating. Now at the pole it's rotating too, but at the pole, it doesn't amount to anything. It means standing at a location at the North or South Pole and just doing this over a 24-hour period. That doesn't lead to much. But what happens at the equator is you've got all that circular motion, and it's a big circular motion that gets completed every 24 hours or so. And so what's going to happen here is there is an acceleration. A person standing at a different latitude, other than the polar region, has an acceleration and towards the rotational axis. And that acceleration means that the measured normal force will be less than mg. Those two forces don't balance, so when we stand on a scale, we'll measure the normal force, and that will be less. Now, one thing, too, I want to point out, I know I need to move on from this diagram, is notice they're using G as a gravitational field. They're saying this is purely a gravitational effect, these little g's that they've included in these diagrams. So I want to continue treating that as gravitational. Okay, here we go. So at the pole, there is no acceleration. N equals mg, and we'll be able to measure that. So at the poles, acceleration is 0, n is equal to mg, and we've calculated that out to be 9.83. At the equator, now this is right at the equator, a couple things we have to consider here. The Earth's rotational period is not 24 hours. And so I don't think we've talked about this so far. I think it's time we have that talk. So if this is the Earth, let's say that the sun is directly over there. And so when the Earth rotates, let's say that it's noon, the sun lines up with the north to south meridian line. And so the sun is directly along the meridian line. And what we're going to do is we're going to let the Earth rotate and rotate and rotate. Now, once we're pointing right back in the very same direction, that would be one rotation. The problem is that's not how Earth's motion works, because there's orbital motion as well. So once we've done one rotation, what actually happens is by the time the Earth has rotated around once, it's moved in its orbit. I am no longer, after one full rotation, directly pointing towards the sun. for example, again. Now, what that means is that the Earth has a rotational period, but what we call 24 hours, what we call one day, is actually a little longer than one rotation, because once I get to here, I'm not facing the sun anymore. It takes about 4 more minutes to line up with the sun. And so it turns out if you look at Earth's rotational period, it's 23 hours, 56 minutes, and 4 seconds. Now, how could I measure that number? And what you could do is, instead of using the sun as a reference, use the stars. So if instead of looking at the sun and waiting until how much time until I'm facing the sun again, look at a star and then find out how long it is until you're pointed towards that star again. And that rotational period represents accurately one rotation, 23 hours, 56 minutes, and 4 seconds, roughly. Not what we call a day. So what we call a day is a little bit more than one rotation by about 4 minutes. Okay, something that you should know, right? You can tell your friends this is what we learned about in physics, Physics 3A today. So when we calculate the rotational period of the Earth, it's 86,164 seconds. Now, the acceleration would be given by v squared over r. Now, up until now, we've been saying that v could be calculated as 2 pi r divided by the period. And so I'm going to plug that in and square it. I am going to come up with a new formula. So in chapter 5, with all of those circular motion problems, we kept using that, saying that acceleration is related to velocity and radius this way. But now I'm going to say, you know, this formula right here is really handy. We're going to be making use of that, especially here in chapter 6. The acceleration can also be written in terms of a formula that uses a period of rotation, period of circular motion, rather than velocity. And so that's a good formula for us, this one right here. So what I'm going to do is I'm going to plug into, well, the 4 pi squared is 4 pi squared. I'm going to plug in the radius of the Earth. I'm going to plug in the period and square it. And what it says is that the acceleration that someone at the equator experiences due to the rotation of the Earth, there is an acceleration of 0.0339. Now, that's not huge compared with 9.8, but it's a measurable effect. And so what you'll notice here is gravitationally, the gravitational field is 9.83, but what we are measuring is that gravitational effect minus this much of an acceleration. And so the normal force is going to, and we've got that here. Yeah, let's go back through the equator and show this, because we got the formula set up here. If we go back to this object at the equator, there's an acceleration in this direction. What we can do is set up the formula. The acceleration is a result of net force divided by mass. When we solve this for normal force, we find that the normal force is going to be less than gravity, and it's going to be less by this amount. It's going to be mg minus ma. So the gravitational field then, the effective, what feels like a gravitational field includes an acceleration effect. So g minus a leaves us then at 9.80. And I'm still not sure why their number says 9.78, but I'm coming up with 9.80 as the measured difference. Now, what would happen also then is that at different latitudes, we will have varying amounts of this effect. Okay. All right. Well, I carried a bunch of significant figures around, and that's the number that I've come up with. All right, so effectively, that's what that would come up to be. What about satellites? Let's say that we want to put something in orbit. How should we do that? And look, here's what we're going to do. We're going to launch something. Oh, look, it's Cape Kennedy, Florida. So here we are launching a rocket, and what we're going to do is fire the rocket, get it up above Earth's atmosphere, and then we'll use rockets to direct that satellite, and we'll get it moving at a really high speed, and we'll line it up with the orbit that we want it to be in. And then what we do is we shut off the engines. So what happens is this: if we launch a rocket, so one of those orbits they are claiming is circular, and I guess it's circular. Maybe it's a little, yeah, okay, it looks circular. So here's an orbit that's circular. Now, orbits don't have to be circular. A more complicated orbit would be what we call an elliptical orbit. Or we could also launch it at a high enough speed, so see how it's still curving, but it's not coming back. So if we launch it at a high enough speed, it doesn't come back. We'll see more about how to calculate that in a couple of chapters. But anyway, here's the planet. Here is the satellite in orbit. Here is the force of gravity. That creates an acceleration. Now the satellite needs to be moving at a certain speed. If there were no gravitational force, that satellite would follow a straight line and just head out. With the force with gravity in place, there is a force, a centripetal force, that continuously redirects the satellite, and that's what maintains the orbit. All right, so let's try an example. This is looking at what we call a geosynchronous satellite. This is a satellite that's in orbit, and it's placed in an orbit at a distance away from the center of the Earth, such that its velocity matches the rotational speed of the Earth. Now, if this is placed in an equatorial orbit, you can actually launch these so that it just stays above the same location. Or I guess a better way to say this is if we place it in an orbit right around the equator such that it is geosynchronous, this is not just circular, this is geosynchronous, then as the Earth orbits, the satellite speed matches that in a way where it stays right above the same point. And that's handy for communications or for satellites showing weather of the region, right? If I can have a satellite that's overhead and it just stays right at the same location all the time, then we know how to communicate with it. It's always going to be in our field of view. So let's get some circular motion kinematics set up. That would be acceleration is given by v squared over r. That's an r, that's a v. I know this is a v, that's an r. This is, can also be written as 4 pi squared r over t squared. So that's another r. Here's an r, there's an r. V squared over r, 4 pi squared r over t squared, that's the period. Now that's going to be equal to the acceleration. And the acceleration is the same thing as the gravitational field. So it's gravity that's creating the acceleration, and specifically the gravitational field tells us what the acceleration will be. So what that turns into then is v squared is equal to gm over r. To kind of fill in a couple steps there. So this was the kinematics. This is the gravitational force equation. And then when we say the acceleration is force divided by m, the little m's cancel out, but the big M stays there. So, it's the gravitational field of the Earth at this location that determines, it creates the force acting on that object. Okay, so these are handy formulas. These are the formulas we want to use. This one we can go in and calculate velocities based on radius of the orbit. This one we can calculate the period. You know, how long will the orbit take from the period. And this is, let me check the time really quick. Maybe we're going to need to take a break before we wrap this one up, because we are, well, we got a few minutes. Let's do this. Let's see if we can finish through this example. So here's the Earth. Here is our geosynchronous satellite. Here's the direction of that centripetal acceleration. Here is the velocity. And the rotational period of the Earth is 86,164 seconds. That's what we were just looking at. Here's the formula that we derived on the earlier page. And here is big G. Here is the mass of the Earth. Plugging all of these numbers in, there's the mass of the Earth. Here is the period. And I guess what we want to do then is come up with a radius. So this formula is going to allow us to calculate a radius of the orbit. And it says that the radius of the orbit, little r, big R is the radius of the Earth. I'm measuring the radius of the orbit. That's a circle. This is measured from the center out to where that circle is located. That's going to be little r. And that's going to need to be equal to big G, big M, over 4 pi squared, period squared, and then all of that to the 1/3 power to get r. And that works out to be 42,170 kilometers. So when we calculate this for the velocity can be calculated as 2 pi r over the period, and that works out to be 3,075 meters per second. So we got to launch this rocket with the satellite attached. Launch the rocket, get it up into a direction where it's headed in a circle, you know, it'll make a circle. We want to get it moving at 3,075 meters per second, and we want to launch it up to a height of 42,170 kilometers. If we match those numbers, this satellite will end up in a circular orbit at that height above the Earth. Okay. Let's do this. Let me stop there. Let's take a break. I think we're due for a break right now, and we'll come back and we'll pick up with this example.